Hello, I'm Michael Max Davis, co-director of Evolution, and here to talk about renewable energies. To start with a brief summary, renewable energies and fossil fuels. If we begin with fossil fuels, this basically boils down to gas, coal and oil. In fossil fuels we have something that's been concentrated over many millions of years that we can extract and make use of that concentrated energy. But there are two disadvantages. One, it's a finite resource. At some point it will run out. And two, in releasing the energy, we're also releasing greenhouse gases into the atmosphere, which is having a detrimental effect on the environment. By contrast, if we look at renewables, here we can see wind energy, biomass or biofuels, solar energy, which in this case is a photo of solar PV but can also be solar thermal energy, a hydroelectric plant or a geothermal plant. The idea of renewables is that they come from an energy source that's never ending, doesn't run out, and they don't release greenhouse gases into the atmosphere. You'll notice that we haven't got nuclear energy here because that is opening up a whole other Pandora's box. As it is a finite resource, it produces a contaminant that's hard to manage, but it does not produce any greenhouse gases. Now, for this talk, we're going to focus on just a few renewables: wind, biomass, and solar photovoltaic. We'll also take as our point of departure the methodology from the book by David McKay, Sustainable Energy Without the Hot Air, released in 2009, where he did the quite innovative thing of taking all renewable energy sources and all of our energy demands and putting them all in one unit, kilowatt hours per person per day, in order to have a good comparison of the space needed to run off renewables. Now we're going to do the same, but we'll take it to the level of a house. Let's say if we have an energy demand of a house, what kind of consequences are there in terms of renewable energies? For this, I'm going to take an electricity bill. This is for a house that I've lived in. We are 2 adults and 1 2-year-old child. What's important to note is that we have an electric boiler. Now, you can think of all the electric appliances there are in a house, from the plasma TV screens to the computers that get plugged in, the mobile phones, etc. As David McKay very astutely says, though, it's a waste to turn electricity into heat. Basically, it takes a lot of electricity to heat up the water in an electric boiler. Now, this is important in that we shouldn't have electric boilers if we're heating water. It'd be better to have a solar thermal panel. However, for this study, we'll take it that we do have an electric boiler and our demand is 236 kilowatt hours in a 32-day period. Note here again, this is for this exercise only. We're not taking into account heating and cooling demands, which is a significant demand in any household. But let's go forward with this number for now. So if we look at 236 kilowatt hours per 32-month days that I need in this house. And let's first look at wind power. Now, wind power we are dealing with. If we have a power required, there is an efficiency factor, around 50%, of how efficient the wind turbine is converting wind into electricity. The other factor is the wind velocity itself, which, as you can see, is dependent on half rho, which is the density of the air times the velocity of the wind to the power of 3. And the other is the area of the blades. In short, the more wind you have and the bigger the area you have to capture that wind, the more power you get. Now, if we bunch up all of our constants, we get 0.255 times the wind velocity cubed times the diameter squared. So in our house, what does this mean? Well, if we take a wind speed of between 4 to 5 meters per second, we need a diameter of around 3 meters. 4 to 5 meters per second is reasonable in Europe, but to catch it we do need to raise our turbine quite high. So in terms of the house, yes, we can do it with a wind turbine, but the wind turbine will be a significant presence next to our house. So it depends if you want a wind turbine or not. Some people do and some people do not. If we then go on to look at solar photovoltaics, here we have a panel that captures solar radiation and turns it into electricity. Let's take the assumption here that we are going to move to a sunny space in Europe, Madrid, with approximately 5.6 kilowatt hours per meter squared per day. Now in terms of our solar panel, we have the power that we get per meter squared. Again, it's dependent on an efficiency factor. In this case, with a pretty good panel, 20% of our sun can get turned into electricity, and then the power that's coming from the solar radiation. Now putting the numbers in and rounding it down to simplify, we have about 1 kilowatt hour over our 32 days, or 32 kilowatt hours per month per meter squared. That means that to get our 236 kilowatt hours per month, we need approximately 7.4 meters squared of solar panel, which takes up most of our roof, but certainly visually less of an impact than our turbine. Let's last now look at biofuels in the 3 that we're going to study for this lecture. Biofuels, again, we need a meterage required to cover our demand. And the meterage that we need in meters squared depends on our monthly demand, the power density produced by our biofuel, and our harvesting period. Now, what I'm going to do here is say let's have a pretty high power density biofuel, such as sugarcane, and take the leap of faith that by clever crop rotation we can harvest every 6 months. Now this gives us just over 1,500 meters squared of crop. If we compare that to our house, it is a substantial amount of land. Basically, we need a farm around our house of sugarcane in order to meet that electricity demand. So, if we're thinking of renewables for the home, in this case be it wind, biofuel or solar PV, we need to think fairly big. We're talking about substantial installations to meet the demand, and remember, we haven't considered heating and cooling. However, the other way that we could look at it is to say not only is it supplying the demand, but if we work with the demand itself, we can reduce not only my electricity bill, but also the amount of space required for renewables. However, in this case, reducing that demand does not depend on a solar panel, wind turbine or biofuel. It depends on the users and the people living in the home. So we get to that we can talk about renewable energies, but in order to really reach a sustainable solution, we don't only look at supply, we also look at demand, and we have to work with the people involved. Thanks very much for your attention, and I hope you found that an interesting journey at dipping into renewable energies.